In this video, we're going to talk about section 10.6 in your book, which is on what's called parametric equations. And essentially the idea is, from 171, all of you should remember an equation for projectile motion, something like h of t equals negative 1/2 gt squared plus v sub 0 t plus h sub 0. If you don't remember that, it's not all that important. We're going to be expanding on that in this section of your book. So we're not going to use that equation, but we're going to use something similar to it. But essentially, if you remember, this was a projectile motion problem where you say take a ball or a rock or a rocket, you launch it straight up and then it comes straight down. And this equation tells you the height h at a given time t, where like v sub 0 was your initial velocity, t was time, h sub 0 was your initial height, and g was the acceleration due to gravity. A lot of times when you see it, this is just negative 16 t squared. And then the rest of that's the same. So we used that equation before in 171. And the problem is, as far as it goes, when we launch a projectile straight up and straight down, well, there's not really much we can do beyond that with that equation. In the real world, that's not what we do. In the real world, we would do something like this. So for the sake of argument, suppose this is a quarterback, Tom Brady, and he's going to throw the football out to Rob Gronkowski. Gronkowski runs this way, Tom Brady throws the football. He doesn't throw it straight up and down. He has to throw it outwards like this. And, well, ultimately, if you wanted to, we could kind of continue this arc. And clearly then that's a graph of a parabola. So if we wanted to, we could, let's see, we'll do it in green. We could put an axis, say right here and right here. And we could define a quadratic, and that would actually model this behavior right there. But again, the problem is, if Tom Brady's throwing a football, and I come up with some equation in terms of x and y that shows me where that football goes, well, it will tell me, say, the distance it goes x horizontally, and it will tell me how high it goes y. But the problem is, if this is, say, actually a real football that you're throwing to somebody, well, if he's running this way, then you need to make sure that when you throw it, it gets to a certain height at a certain time so that he can actually catch it. And the problem is, for any parabola, for any quadratic we come up with, we only have two variables, x and y, which account for the horizontal and the vertical, but they don't add in that other variable time and making sure it goes where we want it to go when we want it to get there. And in order to do that, we actually have to add to our equation a little bit, and we actually have to add a parameter, t. That's where we get parametric equations from. And essentially the idea is, I want to make sure to use the variables your book uses. Let's see. We're going to look at what's called plane curves. I'll explain what that means in a minute. Plane curves. Essentially, plane curves are all points of the form xy where we actually get, your book uses f of t and g of t. Let's say that equals f of t and g of t. That looks a little bit confusing. Essentially, the idea is plane curves are just curves, graphs, quadratics, cubics, any messed up picture you want to draw. They're curves in the plane, in the real plane that we're used to drawing, the xy plane. But our points xy, the x value of any point on the curve comes from some function f of t, and the y value comes from another function g of t. So basically, our x and our y are dependent on this variable, this parameter, t. Again, hence the name parametric curves. When I learned this kind of confused me a little bit, trying to understand what was actually going on. So we're going to kind of walk through a few examples to make sure we're clear on this. So for example, let's see. We will use this. X equals t squared minus 2t, and y equals t minus 2. And essentially the idea is, these are parametric equations. They're two equations for x and y in terms of the parameter t. T we can just think of for most of what we're going to be doing. T is essentially time. So at a given time t that I can plug in, I get an x value and a y value out, and that tells me where it is in the plane at a given time. In order to graph these, the easiest way to graph when you start is to just create a table, just like you do when you first start graphing. Only now we'll have our parameter t, then we'll have x, and we'll have y. One thing to be aware of before we start, since t is time, in a lot of problems there are restrictions on t. T has to be greater than 0, t has to be greater than or equal to 0, things like that. So make sure you're looking at your problems and you know any restrictions on your t. But for this one we have no restrictions, so we'll just pick a bunch of points. Let's see, we'll start with 0, and then we'll do 1, 2, 3, and then we'll look at -1 and -2. And we should get an idea of my graph from that. So, we just start plugging in. When t is 0, x is 0 minus 0, which is 0. Y is 0 minus 2, which is minus 2. When t is 1, we get 1 minus 2, which is -1 for x, 1 minus 2, which is -1 for y. When t is 2, 2 squared is 4, 4 minus 4 is 0, so x is 0, y is 2 minus 2, 0. When t is 3, we get 9 minus 6, which is 3, and here we get 3 minus 2, 1. When t is -1, we get 1 plus 2, which is 3, and here we get -1 minus 2, which is -3. And then at -2, we get 4 plus 4, which is 8, and -2 minus 2, which is -4. Now we just have a bunch of points in terms of x and y. So now we go over to the plane and we plot those points and see what's going on. So let's see. Just list all my points out. I get the point 0, -2, which we'll say is right here. -1, -1. So that would be like right here. 0, 0, which is right here. 3, 1. So we'll say that's about right there. 3, -3, which would be right about there. Maybe 3, -3, maybe a little bit lower. And 8, -4. So at 8, I'm at -4, say down here. A little bit lower. And now what's going on? Well, when we connect the dots on this graph, you want to actually make sure you do them in the proper order. And in this case, since we're thinking about this in terms of time, start with the least value, -2, which gave me this point, then go to -1, then go to 0, which was 0, -2, then go to 1, 2, 3, and there we go, there's my graph. And now obviously these times could keep going negative or positive, so this graph will continue going like that and going like that. And it's clearly just a parabola oriented sideways, just like we were doing in section 10.3 in your book. The one thing that is important here, as far as these plane curves go, again, when we graph them, we're graphing them with respect to the parameter t, and time actually matters, which means all of these plane curves that I draw have an orientation, a direction that matters. In this case, time as it goes forward goes this way. This is time 0, 1, 2, 3, which means the curve is actually going this way. Again, if you think about it, if you think about, say, throwing the football over time goes this way, not that way. If I lateral the ball, then it would go backwards. I'm throwing the ball, so it's going to go forward, something like that. The direction of travel matters because you want to know when the object is here versus when it's here. And is it going to go this way or that way to get there? So when you're doing your plane curves, just make sure to consider the orientation because it matters. As far as it goes for graphing parametric equations, that's pretty much it. It's no different than graphing anything else. Set up a table instead of just x and y, do x, y, and t, pick values for t, check your domain to make sure it's okay, and then find the resulting x and y values from each t. That will give you points, plot them, and you're done. That's pretty straightforward, but if we remember polar equations and things like that, well, when we did polar equations, we understood that the polar equations were just another way of doing rectangular equations. And if the graphs were in the xy plane, then we said, well, why can't I take a rectangular equation and make it a polar equation, or take a polar equation and make it a rectangular equation? And we did that, and essentially it just boils down to algebra. We can do the same thing here. Clearly, that's just a parabola. The vertex is right there. We just finished graphing parabolas, which means we should actually be able to find this equation in terms of x and y, but we can actually do it algebraically using these parametric equations. There are different ways to do this. I'm going to make another video where I do this in a different way, just so we can see different ways to do it. But for right now, one thing you can do is substitution. You have to do what's called eliminate the parameter, which means get rid of t. Because if I get rid of t, all that's left in x and y, and I have an equation. So for this one, pick something to substitute for. I'm going to solve this equation for t. If I do that, I get t equals y plus 2. Now, substitute that in there. I get x equals t, which is y plus 2 squared, minus 2 times t, which is y plus 2. Now I can distribute, simplify, do all of that. I get x equals y squared plus 4y plus 4 minus 2y minus 4, which gives me x equals y squared, 4y minus 2y is 2y, 4 minus 4 is 0. Now that's an equation in x and y. To simplify it so we can see that better, we'll do what we did with parabolas before. Complete the square and do all the math. So let's see. I get x equals y squared plus 2y. Half of 2 is 1. Square that, you get 1. So you get plus 1 minus 1. Just to keep this equal, add and subtract. And then this becomes x equals y plus 1 squared minus 1. Now that's a nice parabola right there. And if we remember our parabolas, well, let's see. This is positive, which means it's oriented upwards, or since this is y squared with x, it's oriented to the right, which is what that graph is. And the vertex, the y plus 1, means I go down 1. The x minus 1 means I go to the left 1, which means I go left and down, and my vertex is right there, which means this is the equation I want. This is what we're going to be doing algebraically, taking parametric equations, graphing them, finding their orientation, and then taking those parametric equations, eliminating my parameter t, so I can get a rectangular equation in terms of x and y. And then I can check and make sure my graph is actually correct, which in this case it is. The last thing I would mention, again, really briefly, this equation in x and y does not have an orientation. It's just a parabola, which we can graph. When you graph the rectangular equations, they have no orientation. When you graph the parametric equations, they do. This one goes this way right here. So just make sure when you're graphing, you know what you're doing. And if you're graphing parametric curves, make sure you put the orientation on there. Like I said, I'm going to make another video where I go through a few more examples of this so you guys can see the algebra and see some applications that we can solve.